Hello all. Today I want to talk about turbulence in multiphase flows. Sorry. Okay. Turbulence in multiphase flows. I know there's been lots of presentations on multiphase flows, but here I'll give a quick introduction. I'm Pranav Mohan and I'm in mechanical engineering at Purdue University, and I'm in West Lafayette. Um, Okay, so before I start, I want to ask everybody a question. So, why is the 5/3 slope from the Kolmogorov's hypothesis important? Can somebody just give me like a brief answer, if you don't mind? So, why is the 5/3 slope important? Anyone? Okay, in that case, I can answer it. So the 5/3 slope is important because it actually represents energy cascading, and it represents how the energy transfers from larger scale to smaller scales. And that is very important because the case I'll be looking at, this slope is followed in some region and it's not followed in some region. So, and another reason is it provides order amidst chaos. As we have seen, turbulent flow is very random, but this 5/3 rule provides some kind of order amidst chaos that we see. So the presentation outline is: first I'll discuss some motivation and application, then some experimental techniques, then theoretical background, results, and followed by some conclusion and future work that could be done. So I quickly want to introduce multiphase flows. I know it's been done in 3 presentations out of the last 9 presentations, but here there are applications in atomization. There are basically bubbly flows in fuel cells and in nuclear engineering, as Drew and Paul talked about yesterday. This is a breaking wave simulation where there's a wave, and then when it breaks, basically it leads to droplet formations, and so it's important. And during this COVID era, how basically the propulsion of our breath, or all the disgusting stuff that comes out of the mouth, how does that come out? So all those fall into the realm of multiphase flows, and it's very important to study the dynamics here. So, just to give us a small motivation, I wanted to show this video here where there are bubbles rising in stratified flows, and you can see. So, at the bottom there is higher density salt with more dye concentration, and you can see as the bubbles rise, there are various eddies that are formed of various sizes, and lots of complicated dynamics is going on here that we need to study and model and understand to be able to model different kinds of multiphase flows. But this is a very nice flow visualization that I wanted to share with you all from my research. So the problem definition is basically when you're looking at flow in a pipe, you can have bubbly flow, you can have single phase flow, you can have bubbly flow and slug flow, etc., etc. However, this presentation will solely focus on bubbly flows that Drew talked about yesterday also. So I want to quickly just give an experimental setup where rising bubbles in vertical columns. So what you have is a vertical column, and there's a test section here that is connected to a pump, and you can basically pump the water due to a pressure gradient in the pump, and the water or fluid, any fluid, can go up or it can go down. Here at the bottom you can have injectors which are shown here, and through these injectors you can generate a homogeneous swarm of bubbles that rise up. And you can also have grid turbulence as well at the bottom to make sure that there is isotropic turbulence in the region that we're looking at. Now, what is important is that you basically image everything through a system called PIV, and I will get into that now. PIV is particle image velocimetry, and what you do here is basically you add some tracer particles in the fluid, and as those tracer particles move, you take high speed images of those, and these are neutrally buoyant particles. And basically you can do some correlation tracking and find out how those particles are moving, and you can know the flow around, for example, a bubble. If you have any more questions on PIV, I can answer them in the questions. But what PIV gives you is a displacement field which looks something like this, and then from here you can go on to calculate. So this is a displacement field, but from displacement field you can go to a vector field, and from there you can calculate your fluctuations and everything that we need to do for turbulence calculations. So Multi-phase flow is very complicated, but this diagram actually, I know this is a very text-heavy slide, but this diagram sums up many of the features of the bubble fluid interactions very well. So I want to quickly go through this figure. This is from 2018, from a figure in paper in 2018 from Annual Review of Fluid Mechanics. So there is an external pressure gradient that causes a mean flow, and this external pressure gradient may also cause relative motion in the bubbles as well. Then you have buoyancy. Buoyancy may lead to relative mean motion of the bubbles, as well as due to the instability of the wake, it may cause some wake-induced fluctuations as well. Now, these wake fluctuations will actually cause bubble agitation in the fluid, and that agitation in the fluid will in turn affect the bubble dynamics as well. And finally, the buoyancy may also generate mean liquid flows, as we saw previously in the stratified flow video that I showed. There might be shear induced turbulence caused by the random motion of the bubbles, and the random motion of the bubbles may cause some liquid flow as well. Finally, T1 refers to the mean flow that generates the turbulence, and the rising bubbles may also cause turbulence. So one of the forces that might be missing from here that was mentioned in 1975 paper is the Magnus effect, which refers to the bubbles spinning in the domain, but that is not something that has been studied yet. But this figure just shows you that there are so many forces and dynamics at play here, and it is a very complicated system to analyze. So we must find which forces are more important than the others and see how basically the energy cascades from larger scales to smaller scales to be able to understand the flow better. So some of the various relevant parameters here are basically alpha, which represents void fraction. In some papers, quality is also used that we all know from thermodynamics. There's also a bubblance parameter given as this, which represents the importance of bubble energy content with respect to the turbulent energy. There's also bubble frequency, and then we have the Peclet number, which represents the ratio of the advection to dispersion. And I'll come to this a little bit later. So first result that I want to look at is basically what happens to the turbulent velocity of water. And as I go through my results section now, you will see a progression from basically 1975 to 2018. So there's a lot of development that you'll be able to see in the results section here. So in this particular plot, from 1975, this at the quality of 0, which is basically single phase flow, you can see that the turbulent velocity is plotted here for the radial position in the pipe that they were looking at, and they see that for different quality, the turbulent velocity might be more or less than the single phase flow. So they basically suggested that in some cases this might be overall there might be a decrease in turbulence intensity due to the introduction of bubbles into the system. However, this was in 1975. However, this is not the case. They came to a conclusion that there is a decrease in turbulence intensity. However, that is not the case, as we will see through some of the results later. So the first, the surprising results that we see here is that, so in this plot, we have plotted the mean velocity of the bubble velocity rising in the fluid versus the average velocity of a single bubble. And as you increase the void fraction, we see that the average velocity of the bubble decreases over increasing void fraction. So the more number of bubbles that we have in the domain that we are looking at, it actually leads to a smaller velocity of the average velocity of the bubbles. And this is counterintuitive, but authors explain it as This could be due to the hindrance mechanism caused by the return flow required to balance the bubble entrainment. So as we saw in the video, as the bubbles rose, there was actually a transport of fluid from the bottom to the top. However, as the different wakes interact, they actually hinder each other rather than so which is why this velocity decreases. Now the authors here also plot for a lot of different they plot from a lot of different papers as well, and they see that for this particular case they do not get good results. Similarly, here non-dimensional dimensional plot is also done, and they see that they get a linear fit with the data that they collected. So the velocity does decrease over various void fraction that we look at. Then we have to realize which forces are more important. So as I mentioned, Peclet number is the rate of advection to that of diffusion, and in this paper in 1975 they plotted the Peclet number, which basically for various void fraction was equal to 2. So this represents that there's a weak dependence on Peclet number, but Peclet number is still more than 1. So the direct mechanism for bubble dispersion is actually turbulent transport of the liquid phase. And then also in this plot, they have these three parameters which basically represent turbulent transport in velocity, turbulent transport in density, and turbulent transport in due to the viscous forces. And they see that so they plot gamma v over gamma vs and gamma d over gamma vs, and they see that both of these plots are actually much greater than 1. So this is a plot on the scale of 10 to the power of 3. So viscous forces are really negligible here, and the turbulent fluid motions are 2 to 3 orders of magnitude larger than the viscous effects that we are looking at here. Then from another paper, and this is more recent, basically what they plot is for the vertical and horizontal fluctuations, they plot the probability density function. And here, this is a semi-logarithmic plot. Semi-logarithmic plot. So the y-axis is logarithmic, but the x-axis is not. To find out what these x-axis means, you can look at the basically the glossary here where I mentioned what each of the terms are. But basically what it represents are the vertical fluctuations and the horizontal fluctuations. In the horizontal side, we see there's a symmetric PDF that we get. So there's not much to analyze there. However, in the vertical fluctuations, we observe that actually there is a first rapid exponential decay, and the curve that we are getting, the PDF, is actually has more positive fluctuations are more probable than the negative fluctuations that we're getting around the mean. And what it shows is that there's a rapid exponential decay followed by a smaller or a less or a slower exponential decay. This result is actually explained more by the energy cascade theory and the energy spectrum, and I will get to that later. I also want to show here basically as a comparison to single phase flow. So here the single phase flow PDF is plotted in the black dots, and you can see that single phase looks like a normal Gaussian fit. However, as we increase bubblance, which is B here, or it also represents void fraction. So as we increase the bubblance, we actually see the probability of positive fluctuations is higher. We also have a autocorrelation plot here, and again we see that so here again the single phase autocorrelation, or what we plotted in for our homework, is plotted here, and also with the bubbles or with void fraction is also plotted. So we can see that there's a stark difference between the single phase flow and multi-phase flow, and in the middle there is a transitional range. Another thing that is important here is that this is done for various velocities of the fluid that we are looking at, and we can see that actually the fluid velocity does not play a role. So the fluid velocity and the change in void fraction does not play a role in how the autocorrelation function looks. It just the only important part is if it's a single phase or if it is a multi-phase flow. Also, I wanted to plot there are some length scales also plotted here. So in the single phase, the mean diameter of the bubble is 5 mm, the Kolmogorov scale is 0.53 mm, and Taylor scale is about 5 mm. But however, when we plot the multi-phase flow, we can see that the Taylor scale actually becomes smaller to around 1 mm, and the Kolmogorov scale length decreases to about 0.01 mm. So it decreases in the order of 1 magnitude. So actually, if you increase and you can see that the Kolmogorov scale actually becomes smaller as you increase the void fraction on the x-axis. So actually, as you introduce more bubbles into the system, you need a much higher resolution to resolve the flow, basically. So now coming to the most important aspect of this presentation, which is about analyzing the energy spectra here. So here the bubble diameter is around 1.6 to 2.5 mm. Okay, and here we have the spectrum plotted for the vertical fluctuations and the horizontal fluctuations, and this is the very interesting part. So first, when we plot the energy spectra for both vertical and horizontal, we observe that there is a -3 slope followed by a -5/3 slope for a variety of void fraction and the bubble diameters that we look at. And the same curve basically follows in both the vertical and horizontal conditions. And this is really interesting because in the 1991 paper, the authors mentioned that the eddies produced by the bubbles dissipate before spectral transfer can take place. So what it means is that at the much smaller scale, in the x-axis, as we are used to, and the x-axis we have the wave number, the smaller scale is still isotropic turbulence. However, in the larger scales that we have, so this is the point where the bubble is. So here LC is 2 mm, so this line is at 2 mm, and this line is at 7.7 mm, and our bubble is around over here. So at the larger scales, basically the eddies and the wakes introduced by the bubbles actually do not cascade energy transfer to the smaller scale. So they actually dissipate through the viscous effects, and in the smaller scales that we have, still the -5/3 isotropic turbulence is followed, which is really, really interesting. So in this particular paper, they actually there's been a lot of debate about this -5/3 and -3 slope. So this is a paper from 2005. So they have various results, and you can see many people have predicted, various different kinds of slopes. However, as coming to 2018, which is where the paper that I looked at was the annual review, they have basically said that now we know robustly that -3 is the slope in the larger scales, and -5/3 is the slope in the smaller scales. Here I wanted to show this another result by Prakash et al, where they plot the power spectral density, which is similar to the energy spectrum that we were looking at, versus the frequency, and they basically found the bubble frequency, which I introduced in the earlier slide, and they found this bubble frequency, and they decided that okay, after this, so all the scales larger than this bubble frequency lead to the -3rd curve, and all the scales positive, smaller than this bubble frequency lead to the -5/3 isotropic turbulence. However, the authors mentioned that this is a qualitative assumption, and the reader should be careful to make any other assumptions or explanations from this, because this was a qualitative analysis that they did. Finally, the possible explanations for this -3rd slope is, people have tried to do some theoretical calculations here, as you can see in this paper in 1991 and this paper in 2010, and both are done through different methods, and they find that okay, they do expect a -3rd slope in the larger scales. So to conclude, I introduced the basic experimental techniques such as PIV. Serizawa et al. In 1975 proposed some incorrect assumptions about the dynamics, which now we know are incorrect. Mean bubble velocity actually reduces with increasing void fraction, which was a weird but interesting result. Inertial effects are more important in bubbly flows. Positive vertical fluctuations are more probable than the horizontal fluctuations. The Kolmogorov scale reduces in bubbly flows, and the energy transfer rate, which is the most important result, is actually different at different scales. So future work could be this result. The only empirical correlations are known for the change in average bubble velocity in function as a function of void fraction. So a theory could be developed for that. This literature is also not developed for stratified flow, so that's something I'm working on. Interaction between the bubble-induced agitation and shear-induced turbulence is also not well understood, and the large-scale mixing effects is also not well understood. So that could be studied. Here are my references, and at exactly 20 minutes, I'm done. Thank you, and please let me know if you have any questions. Thank you.
All right. Time for questions.
Hi, Pranav. This is Mike. I don't know if you can hear me.
Yes, I can hear you. Hi, Mike.
I just had a quick question about the PIV stuff you were going over.
Of course.
Is that, I guess, is that a grayscale image that's generated? I guess I might have missed it, but
yes.
Or is it? Okay, it is grayscale.
I can let me not answer your question yet. So basically, usually most of the cameras used in basically analysis are actually grayscale because actually using all the three RBG actually introduces more uncertainty into the system. So when you're actually doing such kind of analysis, grayscale cameras are best to use because they provide the intensities at every pixel point much more accurately. Now the second thing is this is not an image, this is a vector plot. Or this is a displacement plot. So basically what you do is you basically get your window or you get your image, and basically between two image pairs in PIV you analyze how basically in that small window. So if suppose your window is 1024 by 1024, you find a smaller window of 16 by 16 and you find out, okay, in that particular window where is that vector. So you do that at all the points, and basically you find out how the displacement vector looks at that point, or how the particles are moving in that small window, and then you create the displacement field. So did that answer your question, Mike?
Yeah, Pranav, go back to the next slide. I can help you answer that. No, the previous one.
Yes.
Yeah. Okay, Mike, this is one image recorded by the camera. This is another one. This one is recorded at time t. This one is recorded at time plus delta t. But we need some special cam hardware modification for the camera. So the standard digital camera may not be giving you the delta t needed. Okay, this delta t sometimes could be very small, right? And then you have the grayscale image. You can see the every grayscale spot is an image, right? And then from that each image, you pick up a small window like this or this. Okay. Then you check if these two groups of particles are same group of particles, and using the correlation mechanism. Mainly, this is you should know this is a pattern recognition using the correlation method, right? Then if you do that once, let's assume these two are basically the same group of particles at two different times. The G2 is time t plus delta t, and the first one is t at time t. Then the displacement between these two groups, so this window and this window are separated by a position displacement delta x, okay? If you can find this delta x for every window, every G1, okay, then delta x divided by delta t, you are going to get the velocity. Not only the velocity, but also the vector, okay? Then, Pranav, can you go back to your previous slide? Here it is, okay? Then what is showing here in every, so let's assume you are looking at one position here. If you blow everything up, you'll see there's a small arrow. Okay, this arrow tells you the velocity, magnitude, and direction, 2D way, okay, two-dimensional way. So that's how PIV works, okay? So it can measure the velocity of, so for this image, probably it's more than 10,000 velocity vectors result. from a single measurement. Okay. All right, that's the principle of PIV. Okay.
One thing I forgot to mention is that this image is actually from Professor Steve Verley, who's a professor at mechanical engineering, and I'm taking his course, PIV. So if you're interested in this stuff, you should definitely take his course.
Yeah, this is a very fundamental pattern recognition technique for 2D image processing. Okay, so for pattern recognition. All right, other questions for Bernard?
Hi, Pranav. It's Drew. How you doing?
Hi, Drew.
So, in several plots, you talked about measurements of bubble velocity as well as liquid velocity.
Yes.
Let's see, slide 15. You talk about bubble velocity. Do you know how the researchers measured it for this particular case?
So how are they measuring the bubble velocity?
Yes.
So they are, I believe, so they were using PIV, but they also had LDA, which is laser Doppler.
Laser Doppler velocimetry.
Yeah. So I'm not very familiar with that technique, but they were using a combination of both of them.
Laser Doppler velocimetry is assuming you have a bubble or droplet here, okay, or particle. And if you shine a laser towards this will scatter light, okay? And if you can capture the scatter light to analyze the wavelength, the frequency of the scatter light and also interference pattern, it will get information about size and also velocity. Okay? But this is a point-wise measurement, and you can only get the velocity at a single point. But the previous particle image velocimetry, you can get measurement at multiple points together, hundreds, tens of thousands of particle points together. Okay. So if I understand it correctly for this work, okay, they do experiments separately. First, they only have the bubble, and they use the LDA to measure the bubble velocity, and then they add the tiny particles in the background flow to get the flow velocity using PIV. Okay, that should be the way they did the experiment.
Yes, that's it.
Yeah, and my second question was, so I do experimental two-phase flow. I know that PIV for well-dispersed bubbly flows can be a somewhat finicky issue, because if you have multiple layers of bubbles, you're going to get a significant amount of distortion. Do you know how they're able to measure to ensure the measurements are not being distorted by the multiple layers of bubbles?
So this is planar PIV. So they're only looking at one particular plane. And you can basically, from my experience, you can mask out the bubbles. So you can identify the regions where the bubbles are, and you can mask them out for every frame that you're looking at, and then analyze the flow around it. So that is how it is done.
Yeah, Pranav, I think Drew's question is that if the particles are too dense, can you still do the planar PIV?
If the particles are too dense, so like the PIV particles are too dense?
No, the bubbles.
The bubbles. So that is, that presents as a threshold to basically what is the maximum void fraction you can go to. So that is a challenge.
Yeah, yes. The reason I ask is because you have void fraction percentages going up to 44% on this chart, and I personally think that might be a little outside of that range for well-dispersed bubbly flows, being able to use it for PIV. So I was wondering if they had some other way of controlling for that.
Yeah, Pranav, can you go back to your the PIV results, that Wouter one?
Yeah.
Okay. Yes. Joe, you asked a very valid question. Actually, experimentalists, I do have concerns about this kind of results.
Actually,
if you look at this,
please go ahead.
If if you look at this snapshot, okay, I can easily identify there's a bubble here. There's a bubble here, okay. So if you blow this region up, you will see very strange velocity field. That's not because the flow is like that. It's because there's a bubble, okay. And the valid way should be, at least you should kick out those bubbles before you process the PIV images. But that takes a lot of time, and also it's not a trivial job. And if you have more particles, more bubbles, definitely the light will be scattered everywhere. So you are not going to get a planar image. You are going to get probably the entire tank is illuminated. So that will significantly deteriorate the signal-to-noise ratio. And I agree with you for the result part. If your void ratio is close to 40%, as a PIV guy, for myself, I don't trust the result for that part. Okay, it's hard to accept that's a meaningful measurement. Okay.
So yeah, that might be a challenge actually, but I looked actually for this image. This is actually, there are no bubbles present in this particular image that they're looking at. So this is actually after a swarm of bubble has passed. This is basically the wake that they get.
Okay, that's only the wake.
Yeah.
Okay, if it's the only wake, that's okay. But still,
yeah.
But
there
are some outliers for this image. So yeah. Maybe I should ask Joe to finish his question. Joe, you have more questions?
You kind of covered the bulk of it. My main issue is with the use of PIV for bubble velocity measurements in higher void fraction flows.
It's very challenging.
I'm not gonna eat up all your time. I could keep going.
Okay.
Actually, you can ask more questions, but I mean, yeah, I was focused more on analyzing the results that they were getting than how they achieved the results here. But I wanted to quickly introduce PIV to people.
Can you go to your setup, the setup slide?
Yeah, so this is how they have it.
In this one, does it have background flow or no background flow?
So in some cases they have background flow, in some cases they don't have background flow.
So that means the turbulence is mainly introduced by the bubbles, right? By the rising bubbles.
It will be a coupled thing. So it will be both. It will be due to the mean flow of the liquid and the flow and the buoyant rise of the bubbles as well. So it will be a coupled situation.
There a mean flow moving from top to the bottom?
It can be from top to bottom or bottom to top.
Yeah, do you know the Reynolds number of the mean flow?
So here they were looking at, I think 10,000 is what they were looking at.
10,000. Okay. Thank you.
I will say one more thing. It's extraordinarily important, especially in two-phase flows, to understand the method of instrumentation in which the data was collected, because it's really easy to generate basically superfluous data. Data doesn't provide good information. So if you just look at the conclusions without critically analyzing the way that they generate their information, that can really lead you astray. So for the type of bubble-generated turbulence you're talking about, a lot of work has been done on that, especially utilizing really high-fidelity experiments with like local probe measurements and things like that. So it's really important to fundamentally understand the way that you're generating your data for the model development and for your analysis.
Yeah, I follow what you're saying. So
yeah, that's a great point. Actually, for my philosophy, especially to my students, is always even we do experiment, you need the student understand the modeling, the safety part, and for the safety people who use our experiment data to validate their safety results, they need to understand the technology. Otherwise, sometimes you put mistrust on the experiment data. Okay, I saw that happen again. So Joe's point was a very valid one. So we have to admit that every technology, experiment technology, has its limitation.
Yeah, I agree. This paper had a lot of citations, so I trusted it because of that reason. But I should.
Yeah, it's a old paper 10 years ago.
Yeah.
And it's not an easy job. So we don't blame the authors for not doing something perfect, because we need to pursue incremental improvement. So eventually we are getting better and better results. Okay.
Yes.
All right. I think with that side, I have to close this section. And thank you everyone for this